So welcome to the next topic in IB Chemistry, topic 6, chemical kinetics. And in today's lesson, we'll be looking at 6.1, collision theory and rates of reaction. So these are the learning objectives for collision theory and rates of reaction. By the end of the unit, you should know that species react as a result of collisions, and those conditions for those collisions will be discussed. What the rate of reaction is expressed as, how concentration changes can be measured, what activation energy is, and in terms of activation energy, what a catalyst does. And by the end of the unit, you should also be able to describe the kinetic theory of matter in terms of movement of particles and what that means for temperature. Analyze graphical and numerical data for rate experiments. Explain the effect of temperature, pressure, concentration, and particle size on rate of reaction. Construct something called a Maxwell-Boltzmann energy distribution curve to account for the probability of successful collisions and the factors affecting those collisions. And investigate rate of reactions experimentally and evaluate the results. And finally, sketch and explain energy profiles with and without catalysts. So we're looking at probably activation energy there. So first, what is collision theory? It is also known as kinetic theory, and there are three tenets of kinetic theory. The first one is that particles must collide, and I guess matter is made of particles would be another tenet. That particles must have enough kinetic energy, the energy of movement, to overcome the electron cloud repulsion to react, and this energy that's required to overcome this repulsion is known as activation energy, which you have the symbol capital E and a subscript A. And it's proportional to the temperature. So the higher the temperature, the higher the activation energy. Okay. The particles must also collide in the correct geometrical alignment. Okay, have to be in the right position at the right time. So what is activation energy? Well, essentially activation energy is the minimum amount of energy to activate the reaction, to allow those bonds to break in order for reactants to be formed, for reactants to form products. In terms of the difference between collision rate and activation energy, the factors that mainly affect collision rate are the concentration and pressure of the particles undergoing the reaction and the surface area of solid reactants in the reaction. The factors mainly affecting the activation energy are the temperature of the reaction and also catalysts, which we'll look at each of these individually. The first thing is concentration and how it's related to collision theory. If you increase the concentration, it increases the rate at which particles collide. Essentially, if you look at the images here, if you increase the number of particles, there is more probability that reactant particles, there's more probability the reactant particles will collide in order to form products. Now, obviously, as more products form, the number of reactant particles begins to decrease, so there's then less likely chance of successful collisions. This is why reactions slow down over time, because there's no, basically the number of reactant particles decreases as product particles increase, so there's less probability of successful collisions. So the second aspect of collision theory in terms of potential variables you can change, surface area. So if you increase the surface area, you increase the area for particles that can be in contact. Therefore, this increases the probability of successful collisions. So if we look at these diagrams here, this first one here, you can see that the combined surface area is rather small. So only about 1, 2, 3, 4, 5, 6 particles can be in contact with the surface. Whereas if we have, we break up this large block, you can see now you've got 1, 2, 3, 4 particles attacking each of the smaller blocks. So you have 16 particles attacking, more contact, more chance of successful collisions. The third aspect related more now to activation energy, is that increasing the temperature increases some degree of the collision rate, but more importantly, okay, because you are giving the particles more energy, so there's more chance of successful collisions. But more importantly, it increases the number of particles that will have sufficient activation energy now, okay, to react. Okay, so at the start, if it's at low temperature, you've got a whole number of particles which are moving, but they don't have sufficient energy to successfully collide to form reactants. However, if you increase the temperature, you increase the kinetic energy. That means they now have sufficient energy in the form of activation energy to collide and form products. So temperature is where we bring in the concept of the Maxwell-Boltzmann curve. Okay, so this is the Maxwell-Boltzmann curve. On the y-axis, we have the number of particles involved in the reaction, and on the x-axis, we have the kinetic energy, okay, EK. And as you increase the temperature, you're going to increase the kinetic energy because the thermal heat energy is being transferred to the particles, giving them more kinetic energy. They're going to move faster. Okay? So you can see at 0 degrees here, you're going to have a reasonably small number of particles with sufficient kinetic energy to undergo a successful collision. As you increase the temperature to 25, okay, you're going to increase the number that are going to have the sufficient energy, and as you move on to 100, you will see that the number of particles, this area here, okay, increases even further. So basically the area under the curve is the number of particles with sufficient kinetic energy to undergo the reaction. So as the temperature increases, the probability of the molecules having higher energy increases. The more energy they have, the probability of successful collisions also increases. And finally, we have catalysts. And catalysts decrease the activation energy, therefore increases the number of particles that have sufficient energy to overcome this activation energy, so you have more probability of successful collisions per second. Okay, so in terms of a Maxwell-Boltzmann curve, catalysts basically increase the proportion of molecules in a reaction which have sufficient kinetic energy to overcome the activation energy and participate in the reaction to have a successful collision. Okay, so in this particular example here, I'll do it in different colors. So without a catalyst, these are the number of molecules that can undergo the reaction, and when you have a catalyst, then that number increases by this amount. Okay, so you're essentially lowering the amount of energy required, so that means that there's more molecules or particles which can undergo the reaction successfully. So in terms of an enthalpy level diagram, which we've already looked at in thermodynamics, you can clearly see that an uncatalyzed reaction is going to be require a higher amount of activation energy, and the catalyst basically lowers it by, I'll make it a little bit neater, lowers it by this amount here. Okay, it's reducing the amount of activation energy required in order for the reactants to be transformed into products. So rates of reaction can be defined by equations, okay, and they are essentially the change in concentration of a reactant or product with time. So time is critical, and also the fact it's a rate, it's a change in something over time. So those are the equations there. So that would be change in, that symbol delta, okay, that's what delta means. So it's change in the concentration, so square brackets is concentration. change in the concentration of the reactants over the change in time. And that will also equal basically the formation of the products over a change in time. Because you'll notice there is this negative sign. So basically, as the number of reactant molecules decreases, conversely, the number of products molecules will increase. So there are many rate factors. Okay, there'll be the surface area in relation to solids, concentration or pressure if it's a gas, the temperature and the catalyst. Okay, these can all be independent variables you can control in experiments, and they are found through experimentation. Okay, and it's basically found either through the decreasing of reactants. Okay, that's why we have this negative sign here. Okay, decreasing, or the rate of the increasing products. Okay, how the concentration of the products is increasing over time, or how the concentration of the reactants is decreasing over time. Okay, so notice the negative sign. So what to measure? Well, you can measure changes in gas pressure, okay, changes in mass if it's a solid, changes in color if it's a solution, changes in pH if it's a solution, changes of conductivity if it's a solution. Okay, so these are all things you could be thinking about for your IA. So here's an example of a rate of reaction which is determined by the collection of a gas, okay, using a syringe. This is good for a good setup for gases which are lighter than air, because obviously the gas is then going to rise from the reaction vessel into your syringe. Okay, and how have they controlled their variables? Many ways. Okay, you've got these ideas of an ice water bath to control the temperature. Okay, you've got a block here. Okay, so that kind of controls the insulation also of temperature. So these are all ways that the experimenters have controlled or tried to control the variables. You can also have gas collection over water. This, of course, is not very good for water soluble chemicals, because then the chemicals just dissolve in the water. And warmer water will, of course, decrease the solubility in this particular example. So in this particular example here, we have a slow reaction. So the chemicals are being slowly dropped in over a certain amount of time. There's a reaction. The gas is then bubbled up into a gas jar where it is collected here in this this cavity here. Okay, and it can't obviously go down because you've got or escape because you've got the water there. Okay. You can also have change of mass. Okay, this is good for, say, changing of mass of solids. Cotton wool allows gas to escape but not liquid. It's not great, of course, for gases that are lighter than air, because then the gases are just going to escape and then the mass difference cannot really be captured. Another example which I used in my master's is the calorimetry and spectrophotometry. Okay, the concept of absorbance and transmittance. Okay, so what is absorbance and transmittance? Okay, so you've got this light bulb probably, which is a light source which emits the whole range of the spectra. Okay, then you have a filter which then filters out all the light except one particularly colored light. In this particular case, it is green light. Okay, the sample here is going to then be added, which will only be absorbing in this particular wavelength, and then the difference between what was transmitted and what was absorbed is going to be then detected by a light sensitive cell ammeter, and you can work out basically how much light was absorbed. And then we have here, so we have over time a change of absorbance. Okay, so some chemical reactions like complexes, okay, formation of complexes obviously have particular colors or wavelengths, so you can determine what colors were absorbed or transmitted, and you can then determine if they're being formed or if they are being used in the reaction. Then we have the change in pH or conductivity, okay, using data loggets and probes. Okay, so conductivity, of course, also in solution chemistry. So you can basically see the loss of ions or the formation of ions based on their conductivity. And finally, titrations like acids and bases, okay, where you can see the formation of protons and hydroxide ions. And you can determine the rate of reaction by the loss of a proton, gain of hydroxide, or the loss of hydroxide, gain of protons, or the formation of the salt. Okay. And you also have change, so this is a visual test, so change to a point like clock reactions. Okay, so you basically have a piece of paper with a cross on it. Okay, and basically as the precipitate forms, then you can no longer see the cross, and you just basically time how long it takes for the cross to disappear. Good for precipitation reactions. In terms of mass revision, okay, the slope is change in y over change in x. So the steeper the slope, then of course the faster the reaction, which you can see from the graphs on the right hand side. So in terms of graphical interpretation, due to the uncontrolled effects of temperature and concentration changes especially, the initial rate of reaction is going to be preferred. Okay, so you can either take the average rate of reaction, the instantaneous rate of reaction by taking the tangent of the reaction rate, or the initial rate of reaction. And we prefer the initial rate of reaction due to the points outlined. Okay, so that's the end of today's lesson. Next lesson we'll actually look at these reaction rate equations in a little bit more detail.